Okay, so for section 4.4, I am pre-recording this because I'm not going to be in town when you guys have to do this. And since it's a pre-recording, there will be no entertainment value obtained from me screaming at Henry or Katik or Monica. So this is going to be pretty dry, and it's all serious business. So what you see here is the definition of the Riemann sum that led us to this integral sign. So just to go over things that you've already done in section 4.3, you guys know that this is the Riemann sum. And we concluded that that's equivalent to doing this definite integral. Okay, so remember what the Riemann sum does. Okay, the Riemann sum actually calculates the area of a bunch of rectangles to give you the area underneath a curve. Okay, so let's say if this is your function fx, and you want to say find the area from say x equals 1 to x equals 2, and you want to find this area, then what the Riemann sum was doing was creating a whole bunch of little rectangles, okay, not necessarily of equal width, and finding the area and adding them up. So that's what this summation does. Okay, it adds the areas of the rectangles. This would be the area of an individual rectangle. So clearly this is a painful process to do, as opposed to using this integration technique, and that's what we're going to be learning about in section 4.4. All right, so like I just mentioned, it is easier to do the integration technique because you've got a whole bunch of rules for integration. Just to refresh your memory about what rules I'm talking about, if you go to my website, let's go look that up. And if you go into CP Calc files, you go take a look at Calc Formulas 2. And there are all your integration formulas. So you can integrate a whole bunch of different functions, okay? So that is why this process is a lot easier, better, more accurate, let's say, than the Riemann sum, okay? So what is this slide telling us, okay? This slide is telling us that if you have a function fx and you want to integrate it, then it's the same thing as doing this, where you know that the uppercase fx, okay, is the antiderivative. So uppercase fx, fx is the antiderivative of this. Let me explain what that means. That means that if you have, for example, sine x dx, where this would be your lowercase f, then your uppercase f would be negative cosine x. So uppercase f, this is the antiderivative of lowercase f, which also means that if you were to differentiate this, okay, if you were to differentiate this, you know that you would get sine x, so f prime of x equals sine x, which is your integrand here. Okay, that's essentially what these two lines are telling you. Okay. All right. So actually, what we had earlier was the fundamental theorem of calculus. Okay, also called FTC. Okay, and there are two FTCs. This one is the FTC1. Okay, and FTC1 is just this rule that to evaluate an integral, all you need to do is find its antiderivative and plug in the limits that you have there on the integration. Again, remember that this is called a definite integral when you have limits at the bottom and the top. So let's say we want to do this integral, okay? And so you know that antiderivative rule would be, this would give you x squared over 2, 1 comma 0. Notice that there is no plus c because this is a definite integral. The plus c comes into being only when you have an indefinite integral, when you don't have these limits at the top of this integration sign. So then this gives you, you plug in 1 here, half, and then minus, you plug in 0 there, get half minus 0, which is 1/2. Now in 4.3, actually 4.1 through 4.3, we have learned that what this is actually doing, and I mentioned this earlier, is it's finding the area underneath a curve. So let's go see what this is all about, okay? We've got our xy axis. We've got the line y equals x. Right, there's my line y equals x. And the problem that's formulated here is asking you to find the area underneath this graph and the x-axis between the point x equals 0 and x equals 1. So it wants you to find this area. And the answer by doing integration is 1/2, which makes total sense because if you take a look at the area of this triangle, this base is 1, the height is 1, so the area is going to be 1/2 base times height, which gives you 1/2, which is what this is. So these things kind of make sense from fairly fundamental points of view, okay? We have seen this diagram before, and essentially what it's saying here is that this area that you see in yellow is given by this definite integral. Okay? So one more time to emphasize, the area underneath the curve is the integral between the two limits that are given to you. Okay? All right, so that is really the FTC. So I know you're supposed to do this, and since you're not here, I guess I get to do all the work and have all the fun. And you guys just get to sleep while you're watching my YouTube. Okay, so if I integrate this, my antiderivative of 2x is going to be x squared over 2, because remember the rule is to increase the exponent by 1, divide by the new number, and then I've got this as 1 to 0, plug in 1, you get 1/2, plug in 0, you get 0 over 2, and the answer is 1/2. Oops, my bad. Didn't I F up here? I certainly did. There shouldn't have been this 2. Okay, shouldn't have been there 2. Because when you divide by 2, this 2 and this 2 cancel. So then you get 1 minus 0, which is equal to 1. Okay? So notice how the definite integrals are written, okay? So once you've done the antiderivative, the limits go out here, okay? The limits go out here. So FTC notation, okay? Just to make sure you've got this notation right. Let me see if I can scroll this a little bit better. So, like I mentioned earlier, the notation is that uppercase f is the antiderivative of lowercase f, and then you put your limits like here, okay, b and a. Okay, so specifically, if you take a look at an example, if you integrate this, this is p. So when you integrate x squared, you get x cubed over 3. And then all you need to do is put in q here first to give you this, and then put in p there to give you that, with a minus sign in between them, okay? So make sure you understand that. So if instead of p and q you had numbers, so let's say if you had minus 1 to 1, and you had x squared dx, then this would turn out to be x cubed over 3 from 1 to minus 1. If If you plug in 1, you get 1/3. Minus, you plug in -1, so you get -1/3. So this would give you 2/3. Okay. So all I'm doing is really a definite integral here. So just a statement here that if A and B are numbers, then the definite integral will be a number. If either A or B or both have an x in them, then it's going to turn out to be a function. So take a look at this example here. Okay. So you know the antiderivative of sine is minus cosine, and you put in x equals 1. I mean x to 1, those are your limits. So first you put in x here and you get minus cosine x, and then you put a minus sign, and then you put a 1 in here. Okay, so that'll be minus cosine 1. So you get minus cosine x plus cosine 1. So notice that this is a function. This is a function of x, some other function of x. Okay, because there's an x in there. It's not a mere number like we had in the previous two examples. And the reason why I'm saying this is that later on we're going to do FTC2, where we're going to need that concept that it could possibly be that your answer really is not a number anymore, but is a function. Let's just do more examples of FTC, which is just kind of integrating stuff out. Okay. Let's do this example here. Okay. So again, you need to know your antiderivatives, although I know you guys have the formulas given to you, so it's a matter of looking them up. So if you look at it, I want to find the integral of sec squared theta, d theta. So if I go into my rules here, okay, do I see that anywhere? Right here I see that. Okay, number 12. Okay, number 12. Sec squared u equals du. So remember, instead of x they have u, but it's the same kind of deal. Okay, so if I go back to this, then this is going to be tangent theta, and my limits are going to be pi over 4 and 0. Notice that there is no c here because it's a definite integral. So this gives me tangent pi over 4 minus tangent 0. And from your friends table, you should know this, like all your friends. Tangent pi over 4 is 1, tangent 0 is 0, so this gives me 1. Okay, so again, here comes trig, okay, and here come your friends. Moving on to the next example. Okay, we're doing an absolute value here now. Oh, by the way, it asked you to check using the N box, so let's go do that, okay? Get your TI-84 up, turn it on, clear the sky, make sure the mode is radian, and then put sec squared theta in there. So remember, secant is really 1 over cosine, so you're going to go 1 divided by cosine x, okay, and then you're going to square the whole quantity, okay, because really sec squared theta means sec theta times sec theta. Okay, and I think our answer was 1 before, so let's put this in y1. Let's go graph this, and it's a pretty funky graph. And you're going to go second calc. You're going to go number 7, which you can see is an integral there, and your lower limit was 0, as you can see right there. That's a 0, and the upper limit is pi over 4, so you're going to go second pi divided by 4, and your answer should be very close to 1, if not exactly 1. Wow, it's amazing. It gives you exactly 1. All right. How about doing the next one, which is really kind of a curveball here. This is an absolute value function, okay? So we need to really think about what's really going on here, okay? And you can't blindly integrate the absolute value function, okay? So we've got to really think about this. Okay, first of all, why don't we graph absolute value of 2x minus 1? So here's my xy axis. Okay. I know that my vertex is going to be at 100.